Let us start with today's lecture of soil dynamics. We are continuing with our module 2, vibration theory. Just a quick recap what we have studied in the previous lecture. We have started with multi-degree of freedom system and how to formulate the equation of motion for multi-degree of freedom system we have seen. The mass spring dashpot model for a multi-degree of freedom system, we had considered a 3 degree of freedom system with mass m1, m2, m3 and corresponding k and c values are k1 c1, k2 c2, k3 c3 and our degrees of freedom were x1 t, x2 t, x3 t, 3 degrees of freedom, and applied dynamic loads to each of the units were f1 t, f2 t and f3 t, from which we have drawn the free body diagram for each of these mass m1, m2 and m3, and forces acting for mass m1 are shown here, forces acting for mass m2 are shown here. To maintain the internal equilibrium, we have taken all the forces, and also the forces acting on mass m3 were shown here. Then what we did? We applied the D'Alembert's principle, that is equilibrium of all the forces in the vertical direction, and we had written 3 equations for each of the mass, and that equation was shown like this. So, these were the 3 equations we obtained from the free body diagram by applying D'Alembert's principle. These equations in a simplified format we had written in the form of a matrix. So, how the matrix can be written, which are nothing but the representation of those 3 equations in a better format or simplified format. So, this is the mass matrix, then acceleration vector, then this is the damper matrix, velocity vector, and this is the stiffness matrix, displacement vector, equals to the externally applied dynamic load vector, which we had written in our known form of mx double dot plus cx dot plus kx equals to f of t. So, which is nothing but same as what we had studied for a single degree of freedom system. So, equation of motion remains same, only difference is instead of these values are single numbered, now these are matrices or vector, and the size of the matrix or the size of vector depends on how many degrees of freedom we are considering. So, for a n degrees of freedom system, the mass matrix will be of the size n by n and the acceleration vector will be of the size n by 1. Similarly, the damper matrix will be of the size n by n and the velocity vector will be of the size n by 1. Stiffness matrix will be of the size n by n and displacement vector will be of size n by 1, and externally applied force vector will be of size n by 1. So, in this slide we are showing what we had obtained in the previous lecture, the same thing in the matrix form, and this is the governing equation of motion. Now, in this matrix format, what we had seen, look at the mass matrix, damper matrix and stiffness matrix, all are diagonal. That is, with respect to this diagonal, they are symmetric. And if you carefully look at the mass matrix, only the values are non-zero for a particular degrees of freedom for which we had written the equation of motion. What does it mean? The m1 is non-zero when we are considering the first degree of freedom, that is x1 t. Similarly, m2 is non-zero when we are considering x2 t, m3 is non-zero when we are considering x3 t, otherwise all other entries are 0. This is called uncoupled matrix. We are using a terminology uncoupled matrix. Now, we talked about this coupling in the previous lecture. So, we had taken 2 degrees of freedom system, which is undamped, which is connecting one rigid beam of mass m of varied cross section like this through two springs K1 and K2 to a support, and the center of gravity of the beam is here, that is CG, and we have defined another point which is known as elastic center EC. How elastic center is defined? The distance from the two ends where the springs are connected, if the distances are L1 and L2 from this elastic center to the corresponding springs connected to the beam, then elastic center is defined as K1 times this distance L1 should be equals to K2 times this distance L2. And what are the degrees of freedom we had considered for this beam? Both vertical displacement and rotational displacement. And then we said that let us see what happens if we choose different coordinate system for the rotation. Vertical, definitely we have no choice, but with respect to the initial position, it has vertically displaced, let us say at an instant of time vertically downward. So, this is our reference level, the black line, with respect to which with respect to this datum we have considered case 1, where the rotational axis passes through the center of gravity of the beam. So, it has vertically come down as well as it has rotated about it CG. So, these are the 2 degrees of freedom, and the vertical displacement is y of the point CG, and the rotation about the CG is theta as shown here. So, the corresponding forces acting on the beam are the inertia force m y double dot, because of the vertical displacement corresponding acceleration is y double dot. So, inertia force is m y double dot, and because of rotation the rotational inertia force is I theta double dot. Okay? I is the moment of inertia of the beam, and because of the 2 springs connected to the 2 ends, what are the spring forces acting? This side spring K2 was connected. So, this was K2 and this was K1, and the distances with respect to the CG, we have seen this distance we had considered L1 and this distance we had considered L2 from the CG to the ends of the springs. So, this spring is subjected to the corresponding displacement is y plus L2 times theta. So, K2 into y plus L2 theta is the spring force, and this spring force also will act vertically upward because the net displacement of this point is vertically downward. So, it will try to push it back to its original position. So, this magnitude will be K1 times y minus of this L1 times theta, from which we had seen that by considering 2 equilibrium conditions, that is nothing but applying the D'Alembert's principle for moment equilibrium about the CG and the vertical force equilibrium for all the vertical forces, we can write these 2 equations, which we can represent in matrix format in this way. So, what does it mean? Finally, for this case, when the rotational axis passes through the center of gravity, we got mass matrix. This is the mass matrix, which is uncoupled. So, this is uncoupled. Why it is uncoupled? Earlier we have mentioned we called uncoupled if other than that corresponding degrees of freedom, if all other entries are 0. So, here this is non-zero corresponding to the degrees of freedom of y. Here this is non-zero I corresponding to degrees of freedom theta, whereas other entries in the matrix are 0 and they are diagonal. Whereas, look at the stiffness matrix, this is our modified stiffness matrix for the entire system. This is coupled because for the first degrees of freedom, that is y here, the entry for theta is non-zero. So, theta is also having some effect on the degrees of freedom of y. So, that is why we are mentioning it as a coupled matrix and we are defining this as uncoupled matrix. and as we had seen earlier, the size of the matrix should be the depending on the degrees of freedom. We have 2 degrees of freedom system. So, this size of matrices are 2 by 2 and these vector sizes are 2 by 1. So, this is for the first case. Now, let us see what are the other possible cases for the same problem we can address to. So, in the case 2, let us consider that rotational axis passes through elastic center. The first case we had considered the rotational axis passes through the center of gravity. In this case, we are considering rotational axis passes through the elastic center. So, how the free body diagram will look like? Let us see. Now, we have datum, this one. We had our CG of the beam here and elastic center is somewhere here, EC. And what happened in the new position? It has come down here and it has rotated. We are considering now about its elastic center. So, this is EC, whereas this is CG. So, let us say the rotation about the elastic center is represented as phi. What are the forces acting on the beam now? The inertia force will be, let us say, the vertical displacement, that is from here to here, is u, and the distance between elastic center and center of gravity, let us say, E. So, what should be the inertia force due to the vertical movement on the beam and where it should act? As we know, inertia forces will always act at the CG of the beam. So, because of the vertical displacement, EC has moved down by an amount of u, whereas the CG has moved down by an amount of u plus E times this phi, for small phi of course. So, the inertia force, vertical inertia force will be m times the corresponding acceleration will be u double dot plus E phi double dot. Am I right? The displacement for the CG is u plus E phi. So, the corresponding acceleration is u double dot plus E phi double dot times mass will give me the inertia force because of the vertical displacement. And what is the rotational inertia force? That should be again about this CG, that is I phi double dot. And we had springs at these two corners. So, what are the spring forces now acting? Remember, the distance of this spring from the elastic center were L1 from this side and L2 from this side from the elastic center. So, at this end the spring force should be K1 times u minus small L1 times phi, and at this end the spring force should be K2 times u plus small L2 times phi. Okay. So, free body diagram is complete. These are the forces now acting on the beam. Now, again we will apply our D'Alembert's principle for both the moment equilibrium and the vertical force equilibrium. So, vertical force equilibrium and moment equilibrium about say EC, if we apply and take the equations in the form of a matrix, how it should look like? Let us see. So, the equations in form of a matrix, if we write, it will be M, M E, M E, I plus m e square times u double dot phi double dot plus k 1 plus k 2 0 0 k 2 L 2 square plus k 1 L 1 square times u phi equals to 0. So, after applying moment equilibrium and vertical force equilibrium, that is D'Alembert's principle, we get the equations in this format, where mass matrix and stiffness matrix, if we look at them carefully, what we have obtained in this case, the mass matrix is now coupled, because for the degrees of freedom of u, that is vertical displacement, the entry for the rotational displacement component is non-zero. So, the mass matrix is coupled, whereas look at the stiffness matrix. For the entry due to the vertical displacement, it is non-zero value. However, the other entry because of the rotational displacement is 0 here. So, stiffness matrix is uncoupled in this case. So, by changing our coordinate system for the same beam problem, for the rotational axis, instead of passing through CG to the elastic center, the equation of motion, basic equation of motion changed to the form of mass matrix uncoupled to coupled and stiffness matrix from coupled to uncoupled. So, this is the second case, let us say, and let us select another coordinate system. So, case 3, we are considering the third coordinate system, that is rotational axis is about the corner point, that is the end point of the beam. Suppose this was our initial position of the beam, datum, CG of the beam were somewhere here and EC of the beam was somewhere here. What we are considering now, the new position like this, where we are telling that it has rotated about this end point, about this corner point, and let us say that rotational value is psi and vertical displacement from original position is given by small v. Now, what are the forces acting on this beam? That is, if we want to draw the free body diagram, of course, we know all the forces will act about the CG, the inertia forces. Inertia force due to the vertical movement of this point will be how much? CG we know from this corner is at a distance of L1 and from this corner it is at distance L2, capital L1 and capital L2. And this value of inertia force should be, this value of inertia force is mass times corresponding acceleration. So, what is the displacement of the CG? That is V plus L1 phi, L1 psi. So, V plus L1 psi is the corresponding displacement of the CG vertically. So, corresponding acceleration should be V double dot plus L1 psi double dot, and the rotational inertia force should be I psi double dot. Okay. And what are the spring forces? Spring force at this corner where K 1 is connected, that is simply K 1 times small v, because just v is the vertical displacement of the spring. However, at this end the spring force should be K2 times V plus L1 plus L2 psi. And how much is L1 plus L2? We had considered earlier the total length of the beam is say capital L. So, L psi. Okay. So, this completes the free body diagram of the beam. Now, again we will consider the vertical equilibrium of all the forces and the moment equilibrium about any point, say corner point. So, we are basically applying the D'Alembert's principle once again for moment equilibrium as well as the vertical force equilibrium. By doing that, what we will get the equations, let me write it in the matrix form. If you write the equations in matrix form, it will look like this: m L1 I plus m L1 square times V double dot psi double dot plus K1 plus K2 K2L 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 square times V psi equals to 0. So, this is the form of the matrix or form of the equations, governing equation of motion in matrix form. What we have seen from this, looking at the mass matrix, it is coupled. Looking at the stiffness matrix, it is also coupled, because in the mass matrix, due to the degrees of freedom of V, the effect of psi is present, very much present, it is non-zero. Also for the stiffness matrix, because of the degrees of freedom V, the effect of psi is present, it is non-zero. So, what we can conclude from these three cases for a same problem, the choice of a coordinate system is extremely important for solving any problem, or I should say that to define the equation of motion for any system, the selection of coordinate system is very, very important, because based on the selection of the coordinate system, you can get your mass matrix, damper matrix, stiffness matrix either coupled or uncoupled. So, the behavior of these matrices, that is whether coupled or uncoupled, is not an intrinsic property. It depends on your assumption of the coordinate system. Now, how you may ask that then how we will know which coordinate system will be better? It does not matter. The answer is it does not matter. You can take any physically most appealing coordinate system. What does it mean physically most appealing? That is, looking at the problem, looking at the system, you understand that in which direction or mode shape it can rotate, or in which form it will be more correct way to consider its direction of rotations and things like that. So, based on that you define your coordinate system at the beginning, and then let us see what happens. Suppose by choosing any type of coordinate system, you finally got an equation of motion which is giving you mass, damper and stiffness matrices all are coupled. Okay. So, what will happen? Remember, in the first case, that is when we have solved the basic multi-degree of freedom problem, what we got? All the mass, damper and stiffness matrices are uncoupled. So, that is called the natural coordinate system. So, when M, C, K, all these matrices are diagonal, we are calling it as the natural coordinate system. But if M, C, K are non-diagonal, or let us say in other words, if they are coupled, then it is not a natural coordinate system. So, in that case, we have to do something to transform from our assumed coordinate system to a natural coordinate system. So, let us say the solution x, this is the x vector. Remember, I am writing these as vectors and these are matrices now. These are not the single number. Okay. So, x vector, let us say this is given as phi times z vector. Phi is a matrix which is called transformation matrix. So, if we have considered a n degrees of freedom system, this x vector will be of size n by 1, the transformation matrix size will be n by n, and the new coordinate system z will be of vector will be of size n by 1. What does it mean? X is our chosen degrees of freedom in our assumed coordinate system, whereas z is nothing but the natural coordinate system where we are getting m, c, k all are diagonal. So, we are transforming our assumed coordinate system to the natural coordinate system, because then our solution will be easier. So, that is why we are using an operator which is called nothing but transformation matrix. So, with using the transformation of the system, let us say our new equation of motion takes the shape of m bar z double dot, this is matrix, this is vector, plus c bar z dot plus k bar z equals to vector f bar of t. So, what does it mean? Using the transformation matrix, the new coordinate system, which is we are referring as natural coordinate system, corresponding changes in our mass, stiffness and damper matrices are represented by m bar, c bar and k bar. So, they have transformed from m, c and k to m bar, c bar and k bar. Corresponding force vector also has been transformed to f bar from the original f. And let us say the initial conditions are z at time 0 is given as z naught. Remember, all these are vectors. Okay. These are not single numbered. We are considering generalized multi degree of freedom case, and the initial velocity vector is say z naught dot. These are given conditions to us, and what we said, this m bar, c bar and k bar are uncoupled or diagonal. That is, by using the transformation matrix, we make each of them as diagonal. Now, the form of solution, let us consider it is given by z equals to r sin omega t is the form of the solution for the system. Okay. What does it mean? That means these are vectors. So, we have z 1 is equals to r 1 sin omega t, z 2 is r 2 sin omega t, similarly up to z n will be r n sin omega t. These are assumed form of solution. Now, let us see for undamped free vibration how we can solve the problem. Let us consider the simplest case, then it can be applied to other cases also. So, for undamped free vibration, we are trying to find out the solution. What we have? M bar z double dot plus k bar z equals to 0, because undamped. So, C is not present, C matrix is not present and free vibration. So, F bar vector is not present. What we can write by putting the assumed solution of z, if we write down the equation, it will give us minus r m bar omega square sin of omega t plus k bar r sin of omega t equals to 0, because z we have assumed in the form of r sin omega t. So, obviously, z double dot will be minus r omega square sin omega t, right, which gives us k bar minus omega square m bar times r equals to 0. Now, for non-trivial solution, what we know, r cannot be equals to 0, right. What does it mean? This part should be equals to 0. Okay. What we represent this one, if this is equals to 0, these all are matrices now. So, it means k bar minus omega square m bar equals to 0. That is, determinant of this one should be equals to 0. So, if we find out the determinant, because k is a matrix, m is a matrix, what we will get? We will get, so solving this, we will get the solution in terms of vectors omega 1, omega 2 up to omega n for n numbers of degrees of freedom. What it is called? It is called set of natural frequencies. So, what we got for an n degree of freedom system, it will have n numbers of natural frequency. And another terminology I am adding here, among those n natural frequencies, the lowest value of the natural frequency is called fundamental natural frequency. So, among n natural frequencies, the value of the natural frequency which is the lowest one is called the fundamental natural frequency. And if we want to draw the response, displacement response of this vibrating system, for n natural frequencies we will get n different responses, which are called as mode shapes. So, n mode shapes we can get. Now, from these values of eigenvalues what we got here from this determinant, it becomes a eigenvalue problem, which will give us this value of r, which is nothing but an eigenvector, right. So, by putting those, we will get r vector, which is nothing but eigenvector. So, what does it mean? If we select a solution of say omega 1, that is one particular eigenvalue, corresponding to that we will get the values of r 11, r 12 up to r 1 n, which will nothing but give us what is it? The transformation matrix first element phi 1. Okay? Similarly, corresponding to eigenvalue omega 2, we will get r 21, r 22 up to r 2n, which will give us phi 2. Like that, for omega n, we will get r n 1, r n 2 up to r n n, which will give us phi n. What does it mean? Now, our transformation matrix is ready. So, the transformation matrix is nothing but the phi can be written as r 11, r 12, r 1 n, r 21, r 22, r 2 n, r n 1, r n 2, r n n. So, this will be transformation matrix of size n by n, as we have mentioned. So, like this, using transformation matrix easily for any coordinate system, whatever we have assumed, whatever equation of motion we got, if all the matrices are coupled or some of them are coupled and some of them are uncoupled, what we can transform them to our natural coordinate system, where we will get all matrices are uncoupled or diagonal, and then we can solve it for the n numbers of degrees of freedom, which will be obtained from its natural frequencies, and then the corresponding solution can also easily be obtained. So, with this we have come to the end of our chapter module 2 of vibration theory. So, it ends our module 2 of this course on vibration theory. Now, let us start with our next module, that is wave propagation. For wave propagation, let us first start with the simplest case of longitudinal wave, in an infinitely long rod. Let us see what we can say about these waves. So, this is an infinitely long rod we are considering, and the boundary conditions we are taking like this, that is, what does it mean? We have put the roller connection to the surfaces of the rod, so that it cannot expand in this direction. So, we are considering basically constrained infinite rod in one dimension, in 1D, for one dimensional wave propagation, and the radial straining, that is strain along this radial direction, is restricted by putting these rollers. So, that means we are only talking about the wave traveling in this direction. Okay. So, that is why one dimensional longitudinal wave we are taking care of for this constrained infinite long rod. Let us say the properties of the rod are: rho is the density of the material, E is Young's modulus of the material, nu is Poisson's ratio of the material, and A is cross sectional area of the rod. Now, when wave is traveling, the longitudinal wave is traveling in this one dimension in this rod. Let us take one small infinitesimally small segment with a length, say dx in this direction. So, now we are concentrating on this infinitesimally small segment of length dx, through which the wave is passing through. So, when the wave passes through this portion of the rod, what happens? The stresses are getting generated, and as the wave is traveling through this section, the stress at this end and stress at this end will be different, because the particle is also moving, and corresponding displacement of the particle in this direction, let us say u. So, what are the displacement and stress function for this infinitesimal element within that long rod? Let us see. Let us exaggerate the figure. So, initial position of the particle when the wave is traveling, let us say, was here of length dx, and the final position, let us say, after a time, because this wave traveling with respect to time we are considering, and its position, new position is given by these dotted lines, let us say. When the displacement, this is the displacement u in this direction is given as a function u of x naught and t. So, it is a function of x naught t, which depends on the initial velocity, initial displacement. It is a function of initial displacement and time. With respect to time, the displacement is keep on changing. Clear? And at the end of the element dx, what we are considering? The displacement of this end due to the travel of this longitudinal wave is u plus del u del x times dx. Okay? Here the displacement was u, and the other face at the other side or other end of the section we have chosen, the movement or the displacement of the particle is u plus del u del x into dx. And what are the stresses acting on the element? This side, let us say sigma x naught, which is nothing but sigma x as a function of x naught and t. Whereas, on the other end, the stress should be sigma x naught plus del sigma x naught by del x into dx. Okay? I do not think I should put it here, it should be the differential, right. So, let me rewrite it properly, u with increment del into for that distance dx, that is what we should write. Now, this happens for a distance of dx with the cross sectional area of the element as a. So, what we can write from this, the considering the dynamic equilibrium in this direction of travel of the wave, we can write it here for the stress equilibrium or for the force equilibrium in the x direction, sigma x naught plus del sigma x del x into dx. This is the stress times cross sectional area will give us force in x direction, right, minus this is the force acting on the right hand side of the element. On the left hand side, it is sigma x naught times a. This force, that is the difference of this force between the two ends, it is occurring because of what? Because of the movement of the particle by the displacement of u. So, definitely there is an acceleration associated with it, because we are considering the dynamic equilibrium. And what is that acceleration? Del 2 u by del t square times mass will give us the inertia force. So, this disbalance of the stresses or internal force will be equating with the inertia force of the system. Okay? So, this should be equals to rho a dx times del 2 u by del t square. Actually, strictly speaking, when we are talking about one dimension, you can use d 2 u by dt square also, but when we are taking the multi dimensions 2D or 3D, then it will be partial differential. So, remember this one. So, that one is not dependent on the other, depending on that we have to take whether it is del or d. Anyway, so this is considering the dynamic equilibrium of the system. We can write the internal force equilibrium should be equated with respect to the inertia force of the system. This will give us, by solving, if I keep the previous equation here, so that it is visible. Now, let me solve this one. This get cancelled. Now, area of cross section is non-zero, dx is non-zero. So, a dx get cancelled. We can write it as del sigma x del x equals to rho times del 2 u by del t square. So, this is called basic equation of motion for in one dimension for a wave propagation. So, this is basic equation of motion for longitudinal wave traveling in one dimension. Now, what is sigma x? Sigma x we can rewrite it as, say, some modulus times the strain. stress equals to some modulus times strain, and this modulus m is called for this kind of infinite rod is constraint modulus. Let me write it here, constraint modulus. Why? We have considered one dimensional long rod which is constrained in the direction of its radial movement. Okay. So, it is moving only in one direction, that is in the x direction. So, the corresponding modulus we called as constraint modulus m is given as in terms of E 1 minus mu by 1 plus mu into 1 minus 2 mu times E. So, that is the expression for constraint modulus, and the strain we know strain is given as epsilon x is given as del u del x, because u is the movement and x is the direction we are considering. So, if we put these expressions in our first equation, that is del sigma x del x equals to rho times del 2 u by del t square, what we can get in terms of these two, we can simplify it and rewrite it as del 2 u del t square, that is this side I am writing first, is equals to m by rho, rho goes here, del 2 u by del x square. Okay. So, this is the alternative form of the one dimensional equation what we had written for longitudinal wave. In other words, many times it is written as del 2 u by del t square equals to V p square times del 2 u by del x square. This is the final form of the longitudinal wave in one dimension, where this V p is nothing but root over this m by rho, and this is called longitudinal wave velocity. Wave velocity. Later on we will see this is also called primary wave velocity, okay, which is nothing but equals to root over constraint modulus by the density of the material. And because of this movement, whatever is the longitudinal velocity of wave propagation, longitudinal velocity of wave propagation, and that is V p, and particle velocity say u dot, u dot is the particle velocity which is nothing but del u del t, which can be given as epsilon x del x del t, which is equals to sigma x by m V p, and this will give us sigma x by rho V p square times V p equals to sigma x by rho V p. This is our u dot. So, what does it mean? If the longitudinal wave in one dimension for a infinitely long rod, the velocity of wave is V p, then the particle velocity is given by this stress divided by rho into V p. So, let us stop here today. We will continue our lecture with other directional equations in the next class.